Hello and welcome to a tour of C++, an adamant webinar where you'll learn of modules, concepts, ranges, and a few extra bells and whistles included in C++20. So first, we'll start off with modules. Like the name indicates, modules allow you to modularize your C++ code and to move away from the old C compilation model. You'll be able to define explicitly what you want to import and export. And you'll even be able to split up modules across multiple files and have private sections for your implementation details, where you'll be able to only include declarations in the exported part and have all the definitions in your private sections. Be aware, though, that the implementations as of this talk are still in an early phase. Most of it is because historically there were two different proposals, one from Microsoft and one from Google. Microsoft implemented theirs in MSVC, the compiler included with Visual Studio, and Google implemented their proposal in Clang. Now that the version that's been included in the standard is fixed and final, compilers are adjusting their implementation to match the standard. Okay, so how do you actually write a module? Well, it's not too difficult. All you have to start with is export module and then the module name, and that defines that in this file you'll be defining a module here called math. Afterwards, you decide which elements you want to export. So here we'll export a namespace called math, exactly like this module. Do note that anything nested under the math namespace will also itself be exported. Now, if we want to use our module, we'll just need to say import math. And then in our main function, we can use the math namespace as if it were any normal C++ namespace. Do know that we're also using the import syntax for IOStream, not an include. You can also hide your implementation details by changing section. You can see that in the middle of the file with the module :private semicolon statement. You can name it private, but you can also have different parts of your module that aren't private. Here in this example, we still import the memory module for the unique pointer and make unique function. So in the first part, we have two declaration for functions and our forward declaration for our struct impl. And in the second part, we actually have the implementation for impl and for the underlying implementations of the function as well. This means consumers of the Pimple module will not be able to know what is the layout in memory of that module, and so will not be able to depend on it, nor on its property names, because the only thing they can have is an incomplete type, impl star or stud unique pointer to impl. So one area where you still see that not all implementation vendors have agreed on which compilation model will be the best is that they all have a different one. The standard talks about BMI files for binary module interface. Clang calls them PCM files for precompiled modules, and GCC calls them CMI files for compiled module interface. MSVC just calls them IFC files. So module maps are a very important part of the module's proposal and the module's implementation in C++20 because they allow us to approach the modularization of our codebase in a piecemeal way. Here we see an example module map that's included in Clang's lib C++. So we see it declares a module stud that has the system attribute, and inside of it there is the module iostream, which uses the header iostream. Of course, it's a standard library header, so you don't have an extension, but you would have one. We see it exports explicitly iOS, streambuff, iStream, and OStream, and it also exports start, which means all its transitive dependencies that are in iostream will also be re-exported. Though this is probably not something you want in your own modules or in your own code, this is very, very important to convert existing code bases because sometimes you'll only be included in a single header, but use functions and classes from many different transitive dependencies of that header. Okay, so we'll actually try out modules with Clang++. This requires a fairly recent Clang version, 10.0 at least, which should be Apple Clang 11 point something. The tests here in this talk are done with Clang 10.0.1. The commands used here will most definitely change in the future. But for now, we'll need a few more flags that probably will be required down the line. Okay, so let's start. To compile a module, so the first line is very simple. Just enable the basic warnings and switch to C++2A, which is the working name of C++20. Enable the module's TS, technical specification. So this was the work in progress for modules, the document that specified them. Enable implicit modules. This is to be able to use what are currently header files we can pound include and instead be able to import them like we did with iostream. We also specify the modules map file, so that's the file we saw in the previous slide with the module stood in its inner contents. The module.modulemap file is actually just a file in lib C++. I don't think this will be necessary to pass manually in the future, but for now it is. We also use an option that probably won't be necessary. We pass the emit module interface to the front end, so that's clang-cc1, and to pass that option we use -x clang. So this allows us to generate the module interface file, but probably will become the default in the future. And now how to use the module and compile the main. So we start with the same thing, C++20, warnings, module technical specification, implicit modules, module map file. And then we tell Clang to look for our built modules in the current working directory. So that's the path where we have the PCM file, our pimple.pcm file or math.pcm file. As you can see, we're not passing explicitly a PCM file to the invocation, and then with -o we just generate an executable binary like normal. That file can be run and it will work as any normal C++ file. Okay, Now for concepts. They are also a very long awaited feature since they actually were talked about since the C++OX days, so what became C++11. The implementation has taken a while and the specification thereof as well. What has landed in C++20 is what used to be known as concept light because it doesn't include a lot of extra features that the first proposal for templates had. For example, axioms or concept maps. But it's still very useful. It allows us to express constraints for templated code. It allows us to describe which operations should be valid depending on the type of our arguments. And it allows us to assert the types and the return types of those operations. We can require a concept to be fulfilled, we can compose concepts, and we can overload based on concepts. A very nice addition as well for anyone who's done template heavy C++ is the improvement to error messages that we get from using concepts instead of simply using templates. As they've been implemented and added to the standard, concepts do not have definition checking. We will go back to that later. For now, let's start with the basics. Defining a concept. So we start normally with a template type name T, which is our template type argument, concept, which is our new keyword, and addable, which is the name of our concept. We say that it requires for a variable a of type t and a variable b of type t that the expression a plus b be valid, be well formed in standardese. So a and b here are not actually values or variables in our programs, they're just placeholders that have t as their type, pretty much the same as if you had decl val of t plus decl val of t. To use the concept, you add, after your template is closed, a requires. So here, template type name t requires addable t. And that means inside of the body of our function, we know it's safe to use a plus b. It is well formed. We can combine concepts. So if we have a addable concept and a subtractable concept, we can have a template type name t function, which requires both addable and subtractable. And then inside the body of that function, we know that a minus b plus a is well formed because the concepts require that. We can require the presence of type members. So here we require that the type we are checking against has a value type member type. So in this example, we're using stud vector of int, and the value type of stud vector of int is int, which means it is indeed a member type, and so this passes. We can have more complex compound requirements, and this builds even further on our has value type, where we could require here to have both an iterator type member and a value type member. But this doesn't allow us to say what they should look like. So if we want to check for that, we can actually use a compound requirement which uses braces for a compound statement. That's where the name comes from. And on the left side, you'll have your compound statement with the braces, then an arrow, and then what you want to check against on the right hand side. So here we have t.begin, which asserts that t.begin is well formed for any variable t which has our template type t, and that the type of t.begin is the same type as our t : iterator. So t.begin should return an iterator. That is the one we specified as our type member. This syntax works on G++, but doesn't seem to work on Clang right now. Of course, this may vary depending on where you watch this talk. Clang only seems to support an arrow with a non-dependent type, so you can have arrow t : iterator. That will not work, but Clang will allow you to have arrow void or arrow int, for example. That probably will change in the future. We also make sure that that iterator dereferencing t.begin gives us a type that is convertible to t : value type. So our value type is int, but dereferencing t.begin will actually give us a reference to int, which is not exactly the same as our value type, but a reference of int is convertible to an int by copy, so that works as well. And our template type name t requires is iterable function f can use t.begin and dereference it while being sure what it will give. So I mentioned earlier the error messages. This is an example. This is a G++ invocation with a template error. Instead of calling f with a std vector int argument, we instead mistakenly called it with a simple int argument. And this is the error message it produced. So it tells us that t : iterator is invalid. Well, yes, because int : iterator is invalid. The same for value type. That's normal. And the same for t.begin and the dereference of t.begin. So this is what it gives us. Very clear, very concise, and very simple error message. If you try to do that with Sphinx and static assert and template recursion, your error messages will probably not fit in your terminal window nor in your terminal history. You can have very long template error messages, but concepts allow us to give much more precise diagnostics to the user. Now about definition checking. As mentioned earlier, C++ concepts do not do definition checking. This means templates in C++ are still duck-typed, and requiring that your template type argument is a valid is iterable, for example, will not actually check that in the body of that class you only use operations defined on it. That means you can require a concept but use other things in your class body which will go back to the old error messages that you have without concepts. On the other hand, it's also possible that you've trimmed your class and you removed some functions, so you could actually drop a require statement, but the compiler won't tell you because it doesn't check what you use inside of your class. So you have to be careful to keep your requires and your class body in sync because templates are still duck typed. And the last major feature we'll cover is ranges. Ranges are composable components to map, filter, slice, etc. Ranges of data. They really are an EDSL, embedded domain specific language syntax inside of C++. Very reminiscent of more functional languages. It's possible to use them with iterator pairs or containers. And their design is based on Ranges v3 by Eric Niebler, which is available for C++ 14 and above. The implementation of ranges and what has landed in the C++ 20 standard is much more limited than what Ranges v3 offers, at least for now. It seems, after several attempts at using them, that all compiler vendors are not done implementing them. If you go check on CPP reference, for example, you'll see mentions of a stud_views stream that doesn't seem to be implemented by libc++ or libstud_c++, even in their trunk form right now. So this will again change in the future, but for now, it's still a work in progress, still very alpha. Okay, so a simple range example. So we start with a simple vector of int with 6 values, and we'll define two functions. Our filter lambda, that checks if a number is even, and our transform lambda, which squares a number. And then we'll pipe our ints vector first into the filter view that will filter elements to only keep those that are even, those that fulfill the predicate that we gave it. And then we'll pipe it into the transform view, which takes an int and return another int, takes our filtered int and returns it squared. And then our for loop will work with that and print every number. So a more complex example showing a few more components. So we'll start with iota, which will be familiar with people who've used APL before. It gives us an infinite range, starting from 1 and continuing, well, indefinitely. So this shows that ranges are actually lazy, because otherwise, of course, this wouldn't be possible. We'll then filter our range to only keep the prime numbers. Again, if we were to try to filter something which is infinite, this would also run out of memory. After we've filtered our range, we'll take the first 100 primes. This is not taking the first 100 elements and then filtering which are prime. This is first filtering an infinite list and taking 100 prime numbers. Afterwards, we will reverse the order of our 100 primes to have the highest prime first. Stud_views reverse also does not need backing storage. It does not materialize the array. What it needs is a bidirectional iterator so it can go back once it reached the end. And then we say take the element while they are above 100. This works similarly to filter, but take while will stop after it encounters an element that return false with the predicate, whereas filter will continue filtering the range. And afterwards, we can use our for loop and print every descending higher than 100 prime numbers that we've filtered. Okay. A few extra things which aren't as big features as concepts, modules, and ranges, but still very nice to have. As been done before, the constraints for constexpr have been relaxed. You can now have constexpr destructors, which require that every single data member in your class also have a constexpr destructor. You're now allowed to invoke virtual functions. You're now allowed to have uninitialized variables that you'll be able then to initialize in an if-else statement, for example. Try blocks are allowed, and ASM blocks are allowed, but only in an evaluated context. So a constexpr function can run at compile time or at runtime, and you can have an if statement that will check stud is constant evaluated, which is a compiler helper to tell you if you're running the function at compile time or at runtime. And the try and ASM blocks can be in a constexpr function, but they should only be reached if we are at runtime, never at compile time. Consteval was introduced, so it has the same requirements as a constexpr function, the same limitation, but it is only ever evaluated at compile time. You do not have to check, like in a constexpr function, whether you're running at compile time on runtime. So constexval allows you to force that. And it is an error otherwise. An element can only have one of constexpr, consteval, or constinit. So constinit was also added in C++20, and it asserts that a variable is either zero initialized, so that's a top level variable, or a static variable, for example, or that the variable has constant initialization. That means it can be constructed at compile time. So that's what consteval means. The spaceship operator, which you may know from Perl or Ruby, was added, which allows three-way comparison. So its return value is like the one of strcmp, lower than, equals, or greater than. It can be defaulted if you're writing a plain old C++ class, and it gives you the other comparison operators for free. Now, by default, if you have a defaulted spaceship operator, you will also get an operator equals, the comparison operator. But if you have a user-defined spaceship operator, then by default, the compiler will not give you a comparison operator because it doesn't know what you're checking in your spaceship operator. Maybe you're not checking one of your data members, or maybe there would be a more efficient way to do equality comparisons. You can ask the compiler to also generate it for you by using the equals default that you've known and loved since C++11. All right, that's about it. Thank you. Feel free to ask any questions if you have. And make sure to check out our courses on edmund.cz for C++ teaching or other teaching. Thank you.